Welcome to a new AG session all about analytic geometry. We are to prove that the points given A at 1, 1, B at 4, 1, C 3, -2, and D at 0 and -2 are vertices of a parallelogram. That means if we are going to connect these points, we could come up with a parallelogram. Now this is just a general parallelogram. It's not a rectangle, a square, or a rhombus, which are all parallelograms. Hence, there's only one idea or concept that we need to show to prove that these vertices or these points, when connected, are vertices of a parallelogram. But first, let's try to illustrate them here in this Cartesian plane. A is at 1, 1. Let's consider each grid of this Cartesian plane to be one step, and of course we know that our horizontal axis is our x and this is our y. So 1, 1, 1, 1. This is point A. Okay, let's try to label them later. Next is B at 4, 1, 2, 3, and 4, and 1 here. Okay, so it would seem that this is our, I could label it here, A and B, and it will not be removed later as I label others as well. Next is at 3, -2, but -2 is here, so this is our point C. Okay, that's C, 3 and -2, and finally for our D, 0 and -2 here. Okay, this is our point D. If you're going to connect them with this line, okay, another one here, we could come up with a certain figure which is a quadrilateral, but we are not yet sure if it's a parallelogram. What we are only sure is that it's a quadrilateral. It's a four-sided polygon. Well, you could have another set of analysis to show that this is really parallelogram, but what we're going to show in this video is the representation of the sides of the parallelogram. For any parallelogram, which also again includes rectangle, square, and rhombus, but more specifically for a general parallelogram, okay, it is given that if our figure is a parallelogram, the opposite sides should have the same measurement or same length. Okay, that would mean side AB here. Okay, I'm going to write here side AB. Let me use a segment so that we could come up with measurement. Side AB is equal to its opposite side. You could coin it CD or DC. Just for this case, let me just call it CD so that we could have the correct representation of the parallelogram ABCD. That's how we name it. At the same time, we also have here these two other sides. Okay, we have side BC, or I mean segment BC has the same measurement with segment AD, or let's this case DA, again just to follow the name of this parallelogram ABCD. Take note, this is very different if we're going to have this notation, but of course let me just show the notation. If we're going to use side, just a side, additional information with this, we will not be using equality, we will be using congruent. Okay, it should be congruent to this here because these are segments, and segments cannot be given with equality but for congruence. The same goes as BC. If we're going to talk about the segment, you will be using congruent, not equality. I'm just inserting that for those who have some misconceptions as to this, because if we talk about equality, we're talking about measurements. So there's no label, simply like this. Now, again, for a general parallelogram, the opposite sides must have the same measurement, and if we can show them, then we are now proving, or we're able to show that this quadrilateral here with vertices A, B, C, and D is a parallelogram, and hence the points A, B, C, and D are its vertices. So what does entail if I talk about this measurement? This is actually equal to the distance between the points. So the distance, okay, let me just have a general first. The distance between P1 and P2 is measured as this formula. Okay, we'll have to square the difference between x sub 2 and x sub 1. You square that. And add another similar concept but pertaining to the y value. Now, this is how we solve for a distance. So we'll be solving distance for each of these, and hopefully we could come up with a understanding that these are to have the same measurement as well as this. But of course, even just by inspection, AB, okay, 1 to 3 steps, CD 1 to 3 steps, so it's already okay with this. But of course, for these two, this might not be automatically given. So anyway, let's just show them for all of them. So we have A and B. Let's use, of course, I coined this. We could also have distance of that. Okay, you could also have this notation. We'll have this notation here, distance of that. Okay. Let us just try to be consistent with the given AB so that it will not be confusing. So let us have point B is our second point. Okay, point B is our second point. In short, point B will have the x sub 2 and x sub 1. So x sub 2 is 4. I mean y sub 2 rather. And x sub 2 and y sub 2. That's what I meant with point A. So point B rather. So x sub 2 is 4 minus x sub 1 for A, which is 1. You square that. Plus, on the other side, you'll have here 1 as our y sub 2 minus our y sub 1, which is also 1, and you square that as well. This will give us a result. Okay, we have the square root. This is a 3 squared plus 0 squared. That's actually square root of 9, which will give us a 3 units. Pardon if I wasn't able to show here square root of 9, because a 3 squared is 9, 0 squared is 0. Let me just show it just to have it like this. Square root of 9 and it's equal to 3 units. Take note, we're using the positive square root, not the negative, because we're talking about distances or measurement. So this is a 3 units, just like what I said by inspection here. CD should also be 3 units. So we're going to use here the points for our C and D. Let's use D as our second point. So x sub 1 is 0, x sub 2 rather is 0, minus your x sub 1 for your C, which is 3. And then you square that. Plus, your y sub 2 is negative 2. And then your x sub 2 is also negative 2. But don't forget, it's minus x sub 2, y sub 2 rather. So minus negative 2. Which will give us this result. Square root. This is 3. Our negative, or the square of negative 3. Take note, by double negative property, this becomes plus. So negative 2 plus 2 is 0 squared. Which also gives us a square root of 9 as the square of negative 3. And this is 0, which will give us 3 units as well. In this case, we have now shown that the first two sets of opposite side, or the first set of opposite sides for this given quadrilateral have the same measurement. Okay? Now let's continue with BC. BC. Okay? So let's pick C as our second point. C has points 3 and negative 2. So we have here x sub 1 and x sub 2 rather is 3. And B is 4, so minus 4. And then you square that. Plus, our y sub 2 for C is negative 2. And y sub 1 is 1. You square that. So you have here this one here. That's the square of negative 1. Okay. And this is negative 3. So the square of negative 3. This will give us, okay, that's 1 plus the square of negative 3 is 9. In short, we have here negative, square root of 10 rather. So square root of 10 units. No need to come up with a value in non-terminating number with non-terminating decimal notation, because we're just checking if we have the same measurement with BC and DA. So DA. By the way, if you were able to interchange point 1 and point 2, let's say instead of using C as your point 2, you use B, as long as you make sure that the partners X and Y coordinates would be following this formula, you will have the same result. Okay, so we're almost done. So for DA, let's pick A as our second point. D is our first point. So 1 minus 0 for x sub 2 minus x sub 1 plus your y sub 2 for A is also 1 minus your x sub 2 is for D is y sub 1 rather, sorry, for D is negative 2. So again, don't forget to have minus, negative, and you square that as well. So you will have it here. This is 1 squared plus, that's again double negative property, plus, so you have 3 squared, which again, similar to earlier, 1 squared is 1, 9 squared is 9, 3 squared is 9. So you have here square root of 10 units, which is the same value with BC. Therefore, we have also proven that this is true. With this 2 in line, saying that the opposite sides A, B, and CD have the same measurement, and BC and DA have the same measurement. Or you could also say like this, that segment AB is congruent to segment CD and segment BC is congruent to segment DA. This shows that our figure here, the quadrilateral given here, is a parallelogram, and further shows that points A, B, C, and D with their corresponding coordinates are vertices of a parallelogram. Thank you for watching, and stay tuned for another session here in AG for Analytic Geometry.